I'm Ed Schlesinger, the Benjamin T. Rome Dean of the Whiting School of Engineering, and it is a pleasure to welcome you to Design Day and to have this opportunity to recognize the students, faculty, and staff members whose dedication, adaptability, creativity, and determination helped bring these projects to fruition. Student design projects are an essential experience in our educational program. They all require teamwork, consultation with peers, professionals, and faculty members, and hands-on experiences, which has been particularly challenging this year. And because of this, I'd like to offer my thanks and express my admiration for persevering under these challenging circumstances, and for the exceptional creativity, adaptability, and commitment you have demonstrated. I've had a chance to learn about many of the design projects that are being presented today, and I want to congratulate you on some pretty incredible work. You've done an outstanding job. And I do hope that everyone visits the Design Day website and takes a look around, see what's happening in other departments and what your classmates have accomplished. The need for engineers, the need for solving real-world problems is played out for us every day. Your experiences working on these projects, working with your sponsors, mentors, and with each other have given you skills and expertise that are invaluable. You know what it means to be a practicing engineer, and you have a Johns Hopkins education. Of course, none of what we're seeing today would be possible without our project sponsors. And I want to thank all of you for stepping up, for investing in our students, for mentoring and guiding them, for giving them this experience. No matter what professional path our students may take, what you have enabled has helped prepare them for success, for leadership, and for making a difference in the world. Students, I want to again offer my congratulations. You have made us all proud.
COVID-19 has unrelentingly ravaged the world for the past year.
A mysterious virus.
China's coronavirus
death
like
toll.
15 states.
Coronavirus death toll passes 500,000 after devastating winter surge.
Oxygen therapy through oxygen tanks is the most common treatment for COVID-19. However, oxygen tanks have become scarce in low-resource settings.
But there is another option: oxygen concentrators.
We are Mechanical Engineering Senior Design Team Prime 21, working with our sponsor Luke Chow from Prime Manufacturing Technologies to create an oxygen concentrator for low-resource settings.
Although there are oxygen concentrators currently on the market, they are not intended for low-resource settings.
Our design meets the World Health Organization requirements but minimizes user cost and dehumidifies incoming air to ensure a long device lifetime. These qualities make it ideal for low-resource settings.
Our oxygen concentrator, similar to commercial models, takes in the ambient air, isolates the oxygen, and delivers it to the patient via a nasal cannula.
Our system uses pressure swing adsorption, which alternates applying pressure and vacuum to the zeolite. Zeolite is a clay-like substance that can separate oxygen from nitrogen.
We talked to Dr. Michael Sapatsis to learn more about zeolite. These meetings were important milestones for us as we learned about the significance of zeolite pressurization cycles.
The newly concentrated oxygen leaves the zeolite chambers and flows through a sensor, which outputs the oxygen concentration level to the user interface.
At the end of our year-long efforts, we have created a device that can produce up to 91% oxygen. This reliable production of oxygen has the ability to save lives.
Save lives of the people who don't have access to the medical care they need and deserve.
Save lives of the people with a cost-effective solution for oxygen therapy.
To save lives in low-resource settings.
Thank you.
Thank you.
Thank you.
Thank you for watching.
My name is Eric. I'm a fourth-year bachelor's master's student studying electrical engineering, and I'm working with Professor Susanna Tone on colloidal quantum dot solar cells. My work focuses on designing new materials for solar energy generation, which is a rapidly growing field that is revolutionizing the way our society can generate affordable, clean energy. Solar cells work by generating electricity from the sun through the photovoltaic effect, where absorption of light in a semiconductor excites electrons that carry electrical energy. Notably, silicon shows this effect, and most of the solar cells that we see on buildings or in solar farms are made of silicon, in large part due to its low cost. However, silicon is not an ideal material for solar cells. In terms of physical properties, it is heavyweight and rigid, so it is impractical for applications that require low weight, such as powering cars, airplanes, or mobile devices. In terms of optical properties, silicon is a poor absorber of infrared light, which is bad because a significant amount of energy from the sun is in the infrared regime. We are thus in search of a material that is thin, flexible, lightweight, and can efficiently absorb infrared light. Lead sulfide colloidal quantum dots are a cost-effective material that fits all of these requirements. They take the form of spherical nanoparticles suspended in a liquid, which is like a paint. We can then deposit our solar paint onto a substrate to form a lightweight, thin film. In order to make a solar cell from colloidal quantum dots, several layers with different functions are needed. My research group showed that one of these layers, the hole transport layer, whose function is to transport positive charges through the cell, is currently limiting the efficiency of colloidal quantum dot solar cells. To improve the device performance and the amount of energy generated, we must find methods to improve charge transport in this layer. This was the focus of my research project over the last year. Working with my collaborators, I have accomplished this task through sulfur infusion. By evaporating sulfur atoms onto the ethane dithiol covered quantum dot hole transport layer, we can effectively fill in gaps left by incomplete ethane dithiol coverage. This means that charges are less likely to get trapped within the material. With this method, we demonstrated an efficiency improvement from 8.9 to 10.4%. More importantly, the same strategy could be used in multi-junction solar cells, which take advantage of the infrared absorption of colloidal quantum dots and have higher total efficiency limits than conventional solar cells. With work like ours to improve solar cell performance, we hope that our technology may soon be sufficiently mature to supplement silicon solar cells and to expand the applications for solar energy. Someday, we hope to see our solar paints applied to every surface that receives sunlight, including buildings, cars, and even roads and other infrastructure. I'm excited to be working on furthering the solar energy revolution, and I'm confident that our research and the other exciting energy research being done at Hopkins will have a large impact on the future of our planet.
Imagine that you're going to work, and every day you work in a world with no colors or lights.
Or instead, imagine that you have to do your job in a world with no sound.
或者想象说，当你在工作的时候，大部分的人听不懂你在说什么。Et la plupart des personnes ne comprennent pas ce que vous dites.
At the Blind Industries and Services of Maryland, or BISM for short, most associates don't have to imagine. These are everyday conditions for BISM associates who are blind, deaf, non-native English speakers, and more. Yet their abilities don't stop them from producing a wide range of products such as U.S. Army jackets, notepads, and hand sanitizers.
At BISM, our team was given one challenge: make production information accessible. Knowing production information is an important step towards increasing associate independence. If associates know that they are ahead on their goals, they can decide how they want to aid production without supervisor instruction.
In response, we created a system with three main parts: input, storage, and output. We needed a system that counted how much of a product was being made, stored that information, and then made it accessible to associates. 5 computer science students, 2 mechanical engineering students, and 1 Peabody music student later, this is how we did it.
We began by listening to our users. Our users experienced the world in ways we couldn't begin to comprehend on our own. During our entire process, we regularly checked in with users so that they could lead us to solutions that were natural extensions of their needs, rather than reflections of our own assumptions.
For our first section, input, based on our testing and cycles of user research, we recommend a motion sensor prototype for our input system. Looking forward, we hope to change the device's physical structure to be able to count larger and more fragile items, and wirelessly connect the motion sensor to send information to a database.
For our second section, our storage system, we're currently using a real-time Firebase that's stored in the cloud to keep track of our data. Firebase makes it easy to share data in real time across our app users. However, looking forward, we're considering shifting to SQLite as it's easier to write data to in the long term. We've begun to prototype with this as well.
Our SQLite database converts data from an Excel sheet. We use the database helper to check what's in the database. Then we get our data through an abstraction layer, which accesses information through an adapter. This adapter connects to our code for a mobile app that displays the data. Throughout our process, we made sure that the database can connect to the cloud storage system that BISM prefers. We aim to fully integrate our SQLite database to the input and output method we end up with for our next steps.
Our third section, Output, tested two systems, a mass texting system and a mobile app. From our call-fire texting system, we concluded that the associates would benefit most from an opt-in system with customizable options for how often or when associates wanted updates.
According to our users, the majority rely on their smartphones to send and get information, but not everyone has a smartphone. So the texting system would be a beneficial addition or alternative to the app.
For our mobile app, we first tested visual and audio features. We simulated the app with a Google website from which users could get production information. Associates who could see liked bold colors and large fonts, and those who could hear told us that the initial audio notifications we made were too similar, too long, or too boring. So in response, we created a new set of shorter, more modern sounds.
72 masks, 5% complete.
As we created our first prototype of the mobile app, we kept our users' feedback in mind. Our app has large fonts, simple wording and iconography, bold colors, and more. We've also prototyped a feature for supervisors to organize work teams, as well as a feature for everyone to ask for and give help.
Given the diversity of BISM, the associates' variation of abilities was our primary inspiration behind the flexibility of our designs. For sighted people, colors can help distinguish items in beautiful or fun ways. But for those who don't access colors the way we do, what is the equivalent of colors but for the ears? Music. For the hands, texture. And for design, empathy. Even with engineering, there was no other way we could have gotten to where we are.
Hello and welcome to Johns Hopkins University's Senior Design Day at the Whiting School of Engineering. We are from the Environmental Health and Engineering Department. My name is Olin. I'm here with my team members, Lydia, Jasmine, and Breen, and we're here to present to you about a modular mobile air quality monitoring laboratory.
So a brief motivation for our design project: ambient air pollution poses a serious environmental health threat, leading to millions of deaths worldwide. Common point sources of pollutants are typically caused by human activity. However, the current air quality monitoring system is ill-equipped to detect more localized threats. Many aspects of atmospheric aerosols are still not well understood, such as its impact on air quality on different spatial scales. Typically, spatial characteristics are studied using modeling or remote sensing. However, these methods produce limited data sets since the sensors can only test a small number of air quality parameters with longer time resolutions. Additionally, atmospheric aerosol concentrations can change quickly and vary greatly spatially. Baltimore City and surrounding areas lack in high-resolution, high-quality air quality measurements. Air quality estimates would be greatly improved through the use of a mobile design lab. A mobile air quality monitoring lab would enable researchers to go beyond the detection of critical air pollutants, but rather detect trace gases at high spatial resolution. The mobile design lab should be robust, versatile, and reliable. In order to meet these objectives, a manifold must be designed to accommodate the desired suite of air observation instrumentation. The manifold should be modular and designed with foresight as to the intended and possible uses in the future.
So the three main use cases for our modular manifold include urban air, natural gas, and agriculture. The manifold would measure criteria air pollutants, smog precursors, black carbon emissions, and particulates in urban settings, methane emissions from industrial natural gas operations, and agricultural air pollutants such as ammonia. Our first manifold design is for urban air pollution. This includes 11 instruments, 6 for gas phase measurements, and 5 for particle phase measurements. Because this manifold includes the most instruments, we used its inflow rate to determine the diameters of the inlets for all manifolds.
Our second manifold design is for natural gas pollution. This includes 7 instruments, 4 for gas phase measurements, and 3 for particle phase measurements. Total flow rate required for the gas inlet is 4.1 liters per minute, and total flow rate required for the particle phase inlet is 4.6 liters per minute, with a Reynolds number of 670, which is within the range for laminar flow. Our third manifold design is for agricultural air pollution. This includes 10 instruments, 5 for gas phase measurements and 5 for particle phase. Total flow rate required for the gas inlet and particle phase inlets are 5.6 and 9.6 liters per minute respectively, with a Reynolds number of 1390, which is within the range for laminar flow.
Moving forward, we have a couple of ideas of what we can do with our new manifold. So our manifold we've designed to be future-proof for new rack-mountable instruments. In the future, we can select a vehicle that has appropriate requirements for volume and weight. And in the future, we can also design a prototype that can house this manifold. Finally, implementation and experimentation in the vehicle can allow for modeling and sampling of air pollutants. A special thanks we'd like to give to our associate professor and technical advisor, Dr. Peter DiCarlo, and to our 2 senior design professors, Dr. Heddy Lavi and Dr. Kieran Harmon. Thank you.
Hello, my name is Brennan, and alongside Annabelle Mungan, Lindsay Pitts, and JJ Tia, our senior design project was on filter backwash storage design for Western Branch Wastewater Treatment Plant. Western Branch Wastewater Treatment Plant is designed to treat 30 million gallons of wastewater every day. Western Branch uses 11 anthracite sand filters to meet strict contaminant removal requirements. These filters must periodically backwash, done by pumping water to remove solids that clog the filter media. The dirty backwash water is then sent back through the plant for treatment. An ongoing issue with the facility is inflow and infiltration, that is, millions of gallons of excess water that enter the plant through cracked pipes and drainage. Storms can trigger large flows into the plant that force the filters to be bypassed due to a lack of capacity to treat the dirty backwash water, which then decreases the contaminant removal ability of the plant. Our team was tasked with designing a solution to this to ensure that the plant stays in compliance with contaminant removal regulations. Here are a few photos from our site visit in November of old backwash pumps, the filters themselves, and the secondary treatment process. Now here's a short video that showcases part of the backwashing process.
The final design proposed is a 3 million gallon circular tank of precast concrete with 1.5 feet thickness and the maximal water volume of 2.7 million gallons. The radius is 80 feet, which is the largest the tank can get without risking encroachment on surrounding paths and objects. The schedule is proposed based on WSSC Water's practice, which includes design and permitting phase, the bid phase, pre-construction, construction, and post-construction phases. The process would take over 3 years to complete, over 4 if considering the post-construction testing and inspection. The location chosen is at one available relatively flat area at Western Branch WRF, under various considerations of hydraulics, proximity to main treatment plant, soil type, climate desires, etc. The elevation difference between the filter's tank and the inflow station can be sufficiently powered by only one set of pumps. The soil at the property was determined to be suitable for new constructions, but further geotechnical investigation may be necessary to confirm it is practical for actual application.
This flow diagram shows the pumps and storage tank integrated into the original wastewater treatment plant design. Water enters the treatment plant from the influent station and goes through primary and secondary treatment. Then, dirty backwash will be sent to the new storage tank to be held before returning to the influent station. Treated water continues through the filters to be disinfected before being discharged into the environment. The hydraulic design centered around designing pumps to transport the backwash from the filters to the storage tank. Using the energy equation from fluid dynamics, total dynamic head across the pumps was calculated, and vertical turbine pumps were sized in duplicate at 100 horsepower for the low backwash flow rate and 200 horsepower for the high backwash flow rate. This model shows a side elevation view of the hydraulic system.
In order to determine the amount of solids in the filter backwash, we measured the turbidity during one of our site visits. The turbidity was measured every minute during the backwashing. After taking the turbidity profile, we investigated several solids handling options, including mixing and sedimentation. Ultimately, we determined that the most cost-effective solution for such a large tank would be to manually rinse the tank out when water levels are low. The largest costs of this project were the tank, which was just under $1 million, and the 4 pumps. The costs of calculation and labor over a 20-year period were also calculated, bringing the total estimated cost to about $2.35 million. Thank you. We hope you enjoyed learning more about our project.
Hello, everyone. We're a team of environmental health engineers here at JHU, and we were interested in COVID-19's influence on ambient air pollution. My name is Reed.
I'm Pat Dye.
And I'm Jillian Hessler.
So, the COVID-19 pandemic led to extensive upheavals in numerous facets of our daily lives. One major change was the institution of mandatory stay-at-home orders during the early months of March, April, and May of 2020. During this period, 42 states instructed all non-essential workers to work remotely and not travel to work. This resulted in a dramatic decrease in commuter traffic, so much so that the U.S. Department of Transportation saw decreases of up to 40%. Numerous studies in the past have found significant relationships between vehicle transportation and ambient air pollution, but there have been few opportunities to accurately quantify changes in air pollution as real-world traffic patterns change.
Decreased transport associated with the COVID lockdowns has a direct impact on air quality. So we wanted to focus on criteria pollutants as defined by the EPA that are also highly associated with vehicle transport. For those reasons, we are currently including nitrogen oxides and particulate matter of the 2.5 and 10 micrometer diameters.
So our overall question for our project is, to what extent did the effects of COVID-19 lockdowns make 2020's ambient air pollution statistically anomalous? And our overall objectives are going to be analyze air pollution measurements in order to quantify any changes associated with the COVID pandemic.
We focused on the US because there are robust and recent data sets that are publicly available to us, and also because we are most well versed in what COVID changes look like in this environment as we all currently live within the US. In terms of time, we chose a 20-year period to establish baselines for the trends of our pollutants of interest. For the animations themselves, we used a time period that included the lockdown period while also including enough data to create continuous maps of the continental US. This ended up being the first 6 months of 2020.
For resources, we ultimately opted to use free, professional, and prevalent data available by the EPA, the Environmental Protection Agency, although we did consider some private corporate alternatives earlier on. We also decided to take advantage of some free software for data analysis, such as R and Python notebooks. But we also took advantage of some sponsored professional software through JHU, including Microsoft Office, ArcGIS, and Photoshop.
Some of our deliverables are national and regional trends over the last 20 years, animations of average daily concentrations from January to June of 2020 for our 4 constituents of concern, and chi-square tests for the annual variability of these pollutants.
So these are just some of the observed baseline trends that we noted for particulate matter divided by a region. We decided to divide by region because the continent of the United States is very, very vast. And we divided based on the definitions as defined by NOAA. This established a baseline for the trends that we observed and allowed us to ensure that the changes we observed within 2020 are not simply continuations of overall trends. We wanted to note that 2020 was aberrational beyond these noticeable decreases.
So the chi-square test is a simple test to identify significant differences in variability. And for each of our pollutants, we found the variability to be statistically significant for the year 2020.
So the data provided from EPA source is not continuous. So kriging allows us to take this existing data and calculate estimated values in areas where there are currently no measurements. It's a widely applied methodology to interpolate geostatistic data, and it has been widely applied for air pollution data in particular.
So here is just a brief glimpse of some of our deliverables. This is one of our Krieg maps for nitrogen oxide. But given that we're constrained by time, this is there's plenty more deliverables available on our project repository. So please definitely take a look at that. We wanted to thank you so much for your time and attention.
Warming ocean temperatures strengthen seemingly mundane hurricanes.
New Orleans Hurricane Katrina devastates local farms.
120 miles per hour winds and torrential flooding.
Pollution and ocean warming
That can survive to overfishing
Katrina
previous
devastates
times
local
torrential.
farms.
But something isn't right. Our everyday weather is rapidly changing year to year, and we are seeing more natural disasters than ever. We can't just keep dumping tons of carbon into the air and burning fossil fuels. We need a different source of energy so that the next generations can live in a cleaner, healthier, and breathable world. One idea is renewable energy. Renewable energy comes from replenishable sources like water, sun, and wind. They are some of the cheapest ways we can start tackling a large portion of our pollution problems now. The US Department of Energy predicts that by 2035, wind energy will make up 35% of US energy generated, and by 2050, there will be 100,000 jobs in wind energy development. But how do we find people to do these jobs?
Hi, my name is Willa, and this is why, last year, I started the Hopkins Student Wind Energy Team. Our team is one of 13 teams from US schools competing in the National Renewable Energy Lab's Collegiate Wind Competition.
Our team has been working on designing, manufacturing, testing, and prototyping a fully functional miniature wind turbine. Now, this process allowed us to apply what we learned in the classroom to real issues of today and helps us make the idea of joining the industry more possible.
While we managed the risks of a changing global supply chain and collaborating remotely in the global pandemic, our team was challenged to make a turbine with the following goals. 1. Create a safe turbine. 2. Maximize performance over its power curve. And 3. Make the turbine autonomous.
Our turbine has 4 key subsystems. The rotor and blades use the forces in the wind to spin a shaft. While most teams in the Collegiate Wind Competition build turbines with a single set of turbine blades, our team saw an opportunity in building a second set of wind turbine blades, spinning in opposite directions to harvest the energy shed by the first set of rotor blades.
The generator and transmission turn the energy of spinning shafts into electricity. It is made up of a brushless motor driven to produce electricity, and a timing belt for combining the power from the 2 turbines' rotating shafts.
The electronics and controls monitor the safety of our turbine and adjust the quality of the electricity that our turbine produces based on our needs. It is made up of current, voltage, and shaft speed sensors to monitor wind turbine performance in real time, a microcontroller and linear actuator to manipulate the angle of the turbine blades, a series of power resistors that we are using as a changing load based upon wind turbine performance, and low-level logic circuits to stop the turbine when there is a fault, such as our load disconnecting or when an emergency stop button is pressed.
The structure holds everything together, positioning the turbine into the wind. It is made up of a tower and passive yaw bearing assembly, which uses the forces in the wind to rotate the turbine until it is centered in the airstream. The structure also supports the rotating shafts, generator, and transmission.
We tested our turbine in the Corson Wind Tunnel in Professor Lee's lab on the campus. Our prototype successfully spun 2 sets of turbine blades, and we could monitor our power output with our custom electronics. Here are the results of our test.
Our turbine is safe enough, and it automatically shuts down whenever the emergency button is pressed or the load is disconnected from the turbine.
We maximized performance. We produced positive power at 4 meters per second wind speed, reaching a maximum of 30 watts at 11 meters per second.
Our turbine is semi-autonomous. It executes the desired range of pitches with no user input, and we manually select our wind speed and load values.
From my time with the wind energy team, I learned how to break big projects down into smaller tasks and trust the process. Even small progress each week counts.
If you'd asked me 2 years ago if I was interested in renewable energy, I would have said no. I came to JHU set on working for a company like Boeing, or going into military designer spacecrafts. Through my work with the team, I've really gotten to see all the awesome innovation happening in renewable energy, and I'm more open to it now.
I loved having the freedom to fail while exploring some of the most exciting technological innovations in the industry alongside my peers and mentors, and while building towards the future I want to live in, a better, more livable, more beautiful world.
Hi, we're Team Pulsape, and for our project, we've teamed up with the Maryland Zoo to design an electrocardiograph to measure the heartbeat signals of chimpanzees. Because the current methods of measuring the chimp's electrical signals are quite slow, expensive, and generally require the chimps to be put under anesthesia, we needed to come up with a more efficient and cost-effective way of measuring the chimp's electrical activity. This is really significant because chimps are very prone to heart diseases, so detecting signs of them early on can greatly increase the chimp's survival rate.
This is our device. It's a bar that can read the electrical activity from chimpanzees. When the chimps grab the bar, they complete a circuit that can measure their heartbeat. The idea behind the design is that hanging is already a natural behavior for chimpanzees, so they don't have to learn anything new. So, to go into a little bit more detail about our product. We have a 3D printed box which contains a printed circuit board that acts as the brain for the entire device. The box itself is designed with rounded edges and as few corners as possible to make it difficult for the chimps to grab onto or pry it open. We have a copper pipe around a wooden bar because it has the best balance between conductivity and durability. The copper pipe actually extends a little bit into the box. This is to make sure that we can connect wires from the PCB to the copper without the chimps being able to access it from outside.
From inside the box, our electronics will be able to measure an ECG signal from the copper pieces and send the signal through a cable, which will ultimately be recorded by the computer. We were able to test our device with chimps at the zoo and recorded the following signals. The zoo's cardiologist has confirmed that these readings are useful and helpful for the purposes of monitoring chimp health, and we're really excited for them to continue using our device.
We're making sure to provide the zookeepers with a manual and backup parts so that when we're not around, they can still use our product for years to come. And we hope that when the day comes when there is a potential heart problem with the chimps, the zoo can use our device to make sure they get the right treatment they need in time.